Okay, we're back. I didn't notice that my video recording crashed. So let's pick up where we left on. I actually coded a little bit before I realized it. So let's just go through it. We were actually here when the recording crashed, and what I wanted to say is that we actually want to use this hash move, even though maybe we do not find an entry which has the necessary depth that we need. We want to still use the move that we stored at this position if it's still valid and try it as our first move, since probably this move is one of the better moves that we can search for. And if it is actually in fact the best move, it also guarantees that we have the maximum cutoff down here, since alpha beta search is highly dependent on this move ordering. Right now we don't have any. I'm still thinking on how to get a good move ordering in. Maybe we want to always try to capture stuff first or something, I don't know. But yeah, anyway. Good. So the way I coded this is, so if there's a hash move and the hash move is in our possible moves, because maybe there's a hash collision or something, or the move is not valid anymore for whatever reason, we don't want to use it, then we move it to the front of the array by doing this. I could probably, instead of copying a list over and over, do something nicer, but this is smaller optimizations. We'll do more of this later. So, and then I go through all the possible moves. By running this, actually, does not yield a huge improvement, I found. Okay. Another thing I did in between, a couple of things that I noticed, and maybe we're gonna make this, the rest of this one, a refactor episode, is I changed the board. It was a 3x3 board. Now I made it a 4x4 board to see how far we can go. Let me just revert this just so that we can use the same benchmark. And so this one goes. This one goes. Okay, I could have just done this. Okay, let's do this again. Perfect. Just to see, now we have another using hash move first. It's now a new feature code. We're at ply 13, score -1, -13. This still looks the same, -1, 5.9 versus 6.5 seconds. Not sure if this has any statistical significance or anything. They're actually pretty close. So this one, for example, is 10.3, while here it's only 10.2, and the scores became slightly different, and the best move is slightly different. I assume, though, that 0, 2 and 1, 2 are both the same. 0, 2 is capturing this one, and 1, 2 is capturing this one. Yeah, so I actually think let me just run for another one. 17. This one is similar. 24. This one is a bit faster. So yeah, it helps a little bit. Okay. Another thing I noticed is while testing, I found that we probably always want to print these stats in a sorted way, otherwise they will look fairly random all the time. And then I also realized I really don't like this loop where we instantiate a new instance of the AI and whatnot, so maybe we will move this performance testing function into our AI class. At least to some degree. So let me just, I will commit these changes as they are as the end of last episode. So this is now the implementation of the hash table. What did I change here? This seems to be the formatting that didn't work. Here's the sorting. Here I played around with an empty board. Okay. Let's do this. And then EP9 with hash move, usage of hash move. Okay, cool. Now, okay, let's do. There's a couple of things I want to try and do. Maybe we see how much we can do on a little bit random node. So get best move is nice, but we want to somehow make this terminate after a time. So I want to have a couple of functions here. So for example, def get best move time, which would take a board and time, allow time in seconds. Something like this would be nice. So we can use this to play against it. We can say, okay, we only give 30 seconds per move. I want to have get best move depth. So this would be a board and takes a depth as a parameter. These two functions. And what should happen is we want to remove this max depth parameter. We don't want this anymore. Let's implement by depth first. This is easy. We can do this. This one we just take here the depth parameter. Something like this. We always want to reset the stats. We want to store the principal variation. Maybe, not sure. Hash table stats, I also, so. If we just hand in a board, I don't know, this function could probably go. Yeah, let's remove this one for now. Okay, why is this? Nothing has changed. I just renamed this function. But let's get best move depth. I renamed this function. I added this max depth as a parameter. And then so let's see if this still works. Okay, this is crazy fast, but I think partly because we now do not reset our hash table anymore. We are at 19 after 2 seconds with -8. Yeah. So, wait, which one is the first one where we should? 6 seconds at 15. Half a second. I think what we have now, hash exact 41. Yeah. Look how deep we can go. Bam. In just, I don't know, almost no time. This is a bit strange that this takes 18 seconds and this only 9, but what we now do is in between our perf iterations, we do not reset our hash table. So now you can see that in between all of these, the moves are cached. So this is much, much faster. Our hash table size is just growing and growing. Bam. Look how far we came from searching to 15 with our vanilla alpha beta search to now being at 21 in almost no time. 55, now at 22. Yeah, this time is cut down. It's interesting though that here we actually said we're gonna lose as the best move, and here it seems to think different. Potentially we might have hash collisions or something. Let's see if we kill this, exit. Here yeah, here, if we actually reset the hash table before each search, and we let the search, and in the meantime we can continue. So here we have an allowed time in seconds. The next thing I want to check is if actually we get any benefit from something called iterative deepening, which is exactly that. From the outside, when they call get best move, we do reset the hash table, but in here we would have a loop which is for I in range depth +1 because we want to include this one. And then here we would search to depth I. And now you might be wondering why would we want to do this? So if we search to depth 1, 2, 3, and 4 without resetting the hash table, we already have twofold things. We have a better hash move because, while searching to depth 1 we found the best move, and then next iteration we will take this move first. And the deeper the tree gets, the better it is to just start with the best move first. So basically we'll search the principal variation all the time at first. And then later on, yeah, we can even maybe make this better. I'm not sure if this will help us much with our game, but let's see. 18, we need to go to 21. This will take some time. Okay. Let me think. Good. There's a couple of things while playing against the AI, which I noticed are not so nice. So run game, get best move. This one we need to refactor before it works again. Yeah, alpha beta. We don't need to initialize this anymore. Input, where's our move? So I realized that after doing our move and then after moving as a player, we do not print a board, and sometimes the AI takes quite some time to think. Okay, let's implement this one real quick. So what we're going to do here is basically the same we do in this method. So for now I'm going to copy it. Later on we can unify it again, and we have a allowed time in seconds, so we can import time, and then we can say we start with self start time equals time. This is when we start our search. Here we can essentially say while time minus self start time allowed time. Let's just see if this iterative deepening has any we should also always search in increments of 2, because as you saw before, if depending on whether we stop with our own move or our opponent's move, we get a different situation. And I think if we always move 2 pieces, then it's back to our turn, and we didn't stop at a point where we just captured something and then everything looks good. In the usual engine, you do something like a quiescent search, or I don't know how to pronounce this. where you would search until the depth that you specified, but then you would still resolve all the possible captures and wait until nothing can move anymore to avoid the situation that you just throw over your stack. Half of the board belongs to you, but you do not see that if the opponent then throws over his stack, everything belongs to him. Something like this. Okay, let's just check real quick. This looks good for us. So yeah, if we always go to a depth number which is even. So let's see, perfect. The next one should be, okay. Now we need to also store this. And here, okay, so why not resetting the hash table? Something is a bit fishy. Let's see if our iterative deepening also has the issue. At the same time, we want to go to this maximize function, and every time we are here, let me just think a second. What I need to do now is, in order to implement time, we need to check every time we want to maximize something, we need to check if the time is up. So first of if self allowed time and time minus self start time. Bigger self allowed. Technically, we will be a little bit over the allowed time, but let's not split hairs. So, we need to abort this. Let's just see. This should potentially work. If we now say we need to do this initialization all the time. This is, it's a little bit ugly again, but let's just see. For time, and we want to have time in seconds. So is time in seconds or milliseconds? Let's find out in a bit. So here, let's say 60 seconds, 1 minute. Okay. And then let's just see, there's a couple of things we still need to do. Let's just print this as well. And the stats. And okay, return move score. Okay. So we do not reset our hash table, something breaks. We need to figure out what that is, and let's test if this is working. But one thing, other thing I want to do before we do this is, so I found that this printing that we do in our perf function here is actually really nice for printing when we do a move. So let me move this in here, and then let's have a parameter for perf. Oh yeah. This one can go. This one is the depth move score. Start time. Time. Okay. AI, self, stats. PV. We also need to fix our PV. Okay, this is one thing. Let's just see real quick. This is still working. Yeah. Okay. Here, max 10. True. We don't need this anymore. Whoa. What's happening here? Oh. Na gut. I see how this is annoying. Also, yeah, this is because this one changed. Okay. And is this still roughly the same that we had before? 15 minus 1 minus 15. Okay, this is good. Now we print the perfed inside, which is nicer because I want to do, and forgive me all this copy pasting, we will clean this up. Just like everything that we cleaned up so far. Show perfed false. And here we do. Okay, and then one thing we changed is now this is with relation to total time. Okay, let's just leave it like this for now. Always so many things that I didn't think about come up when I do this, but I don't want to spend so much time on this, thinking time. Okay, if we now do this, okay, let's just play our game. We want to do 0, 2, and now we actually get some output, which because of the long PV is a little bit ugly, but let's see if it stops after roughly 60 seconds. There's still one thing that is not quite correct, so if we return this here, we actually store this score in our hash table, and then we would think this is actually a winning condition for the other player. So this is wrong, but up here in this loop, we should make sure that if our time is up, that we do not use the latest round for determining the best move. And just see what happened here. Anyway, this looks okay-ish at around 20. So this is the score that we returned because of our cutoff. We're still lucky that we chose this as the best move. 60 seconds feels slightly long to play against, but it's fine. At least we see that it's doing something. Yeah, I do too many things at the same time. So, okay. First things first. What we want now is that we just return. Let me see. Maximize is called here, and it is called here. And here we would have to check 2. Yeah, probably we want to have. So here we just return. It doesn't matter what we return, because at the point where it's called, and I have to think this, there needs to be a better way. We will forget to change this at some other place, but here we just break the loop. We stop searching. And then technically here again, this is ugly. There's a better way. I will look it up in my chess engine. If the time is up, we do not break. And here we need to say best move, best score, move, score, best move, best score, and then this one. Okay. So now this should work. No, it's fine. One more thing that we want to say. So currently in our hash table, we just look up for the exact table whether we found it, but of course we actually are also interested in all the rotations, flips, and what you can't imagine. Maybe I should make these output lines a little bit smaller. Here he says he's winning in 20, which is correct. So if you remember here on 21, he says he's losing starting from the position that we just made a move, and now we made a move, and then he says in 20 turns I will win. And here we have local variable, principal, variation, reference before assignment. Where is it referenced? I wonder. Down here maybe? Oh, yeah, it was not assigned. Okay. Just a pity. Now we have to do it again. Let's actually. Let's do it like this, so it will print an empty list if there's no more. Let's print the top 4 moves. 0, 2. This episode is also getting long now. We did a lot of stuff to make the code more dirty. Maybe I will clean it up a little bit off camera and then just tell you guys what I did afterwards. I think, yeah, I want to clean some of these things up. Pew. So, okay, after 60 seconds in depth 21, we didn't return a move, so we actually played this one. Which seems correct. So, how did that happen? Cannot move on top of other player. Oh, yeah, okay. This introduced quite some bugs. I need to actually double check. Maybe we can do together. Git. My repository. One thing I'm quite curious about is how we implement. So you see, here we had quite some stuff. The code is also super messy. Like this is I wrote when I was in university. Add timing here. Time check. If time check is 0, stop search. Okay, let's see. Stop search. We do. Where are we? Well. Yeah, so I think every time we enter our search function, we need to check. If we need to stop, we set a flag, and then everywhere where we actually execute moves, we need to check whether we should still continue or whether we have to stop. And this is also something I want to implement now. When we search for our principal variation, so the moves that have the best score, we actually want to go through our hash table and go through the hash table executing all the moves until we have the position that we were interested in. So, okay, one thing I introduced here is just to not leave it unfinished. If we break here, we actually also need to undo the last move. Okay. Next time I think we will do an episode where we just clean up some stuff, and then from my side I think we can just leave this here as it is. We could do some move ordering or whatnot, but maybe I will just read up on Monte Carlo tree search. We will implement this as well and then check which of the algorithms works better.